Hello everyone, and welcome to the Lab Extension Post Lab. So, using your calculator, you figured out the slopes of the tangent lines to the position versus time graph. In other words, you found the instantaneous velocities at a bunch of different times for your disk rolling down the incline. And when you made that graph of velocity in centimeters per second versus the time in seconds, you got a very linear graph. And not just linear, but it went through 0, 0, which means that the velocity is proportional to the time. So there is definitely a relationship for the velocity and the time for an object which moves like the disk rolling down the incline. This proportionality means that if you double the amount of time you allow it to roll, it will be going twice as fast. If you triple the time, it will be going 3 times as fast. If you quadruple the time, it will be going 4 times as fast. It's just a nice one-to-one direct proportionality. Since we have a linear graph, we can create a y equals mx plus b math model. Our y variable, what we graphed on the vertical axis, is the velocity. That equals the m, which is your slope. Put your number in here if you're taking notes. Don't put the number sign. I'm putting that in there because there isn't a set slope, because it depends, as we talked before, about the angle of your track. Units, rise over run for slope. So the units of rise are centimeters per second, and the units of run are seconds. Now, before we complete this math model, here is probably the most important question in the whole unit to understand, which is, what the heck does this slope actually mean? What does it tell you about how your disk rolled down the incline? Well, let's think about that for a second. Okay, what does that slope mean? How many points does it take to find a slope? 2. How do you find that slope? You do rise over run. Now, this is a graph of velocity versus time. So what does the rise tell you? The rise tells you, velocity axis, how much your velocity changes. And the run tells you how much your time changes. So the slope means how much your velocity changes every change in the time. So let's say you had a slope of, just to use a round number, 1 centimeter per second in this lab. What would that tell you? Well, it would tell you that your disk increased its velocity 1 centimeter per second every second that went by. How it's telling you not what velocity you're going. It's not telling you how much you've changed your velocity. It's telling you how quickly you're changing your velocity, or how fast your disk sped up. That's a pretty complex idea right there. And it's complex because the slope of a velocity time graph is actually the slope of a slope. Because velocity, remember, is the rate of change of position. It's the slope of a position versus time graph. And this number is the slope of a velocity versus time graph. So it's the slope of a slope. It's the rate of change of a rate of change. So again, it's how quickly your velocity is increasing. We're going to work a lot on this in this unit to try to understand this number. Now, this number does have a special name, and hopefully you realize what that name is. We're going to call it the acceleration. So acceleration we're going to denote in an equation with a lowercase a. And so this is the slope of a graph of velocity versus time. And notice here, the a, it does have an arrow over it. It is a vector quantity, although the vector nature of acceleration is a pretty tough cookie. So we have to do an entire activity to figure out what does it mean to have a positive and a negative acceleration. Now, we can translate the words into symbols, because if it's the slope of this graph, we know that rise is the change in the velocity and the run is the change in the time. So saying that the acceleration is the slope of a graph of velocity versus time is the same as saying the acceleration is the change in the velocity over the change in the time. Which leads to a second definition, a more mathematical way of saying it. Acceleration is the rate of change of velocity. How quickly your velocity is changing. So it's not how fast you're going, it's how fast you're getting faster. I know, that's pretty deep, right? It's pretty deep. Now, you might notice that I didn't bring up acceleration in the constant velocity unit. Why? Because if you're going at a constant velocity, what's your acceleration? What's your rate of change of velocity if you're going at a constant velocity? Hopefully you're screaming at the screen, 0. Because if you're not changing your velocity, there is no rate of change of velocity. So in constant velocity, there's no acceleration, and therefore there was really no reason to bring it up till now. Acceleration is only an important quantity when you're talking about how fast something is changing its velocity. Okay, so with that said, let's finish our math model here. First of all, let's simplify these units. Okay. A centimeter per second, this horizontal line actually means divide. So this is a centimeter per second divided by a second. And dividing by a second is the same as multiplying by the reciprocal. And the reciprocal of seconds is 1 over a second. So this is centimeters times 1, which is centimeters, over seconds times seconds, which is a second squared. So our acceleration units are distance or position over time squared units. Okay? But one thing about that is it's kind of hard to interpret. It actually makes it harder to understand what the number means. It's a little easier if you look at the original units and therefore where they came from, the slope of the velocity time graph. So I'm trying to give you a context here for what acceleration means. By the way, you might sometimes see them in a little different. If you're talking about a car, say, you would probably talk about miles per hour per second. So how many miles per hour does it speed up every second? Right? You wouldn't do miles per hour because in an hour your car could speed up an infinite amount almost and probably blow up the engine before it would do that. So miles per hour per second might be how you write it, and then you can't combine the units. But traditionally it's kind of like this, centimeters per second squared or meters per second squared. Now, this is the y variable equals your slope. The x variable is, of course, time. And your y-intercept was essentially 0. What does that mean? Well, the 0, 0 point on a velocity time graph means that at time 0, you have 0 velocity. In other words, it started from rest, which is hopefully the way you did the lab, right? You didn't give it a push and get it going. You just released it from rest. So this is your specific math model. Okay, now let's generalize a little bit. Here's the kind of graph we got when we were starting from rest. But what would change on this graph if we started the disk a few centimeters behind 0? So maybe we put a 0 mark on there and then we moved it further up the incline. Well, think about what would happen. When we got to our 0 time mark, it would now already be moving. So you would end up taking this graph and shifting it upwards. Don't worry about this. This is a demo for class, right? You would shift it upwards. Now, it would still accelerate just as fast. It would still speed up just as quickly, so these would be parallel, but it would have a different y-intercept. Because what does the y-intercept of a velocity time graph show you? It shows you your initial velocity. And think about it. Here's the time axis. The y-intercept is your velocity at time 0. That's kind of what it means to have an initial velocity. And look at the symbols. Just like we did in the constant velocity unit where we said initial position was x sub o, initial velocity is v for velocity sub o for 0 or original, however you want to look at it. So this is the initial velocity. So now that we know all about velocity time graphs for the disk, let's make a general math model that represents the motion of the disk down the incline. Again, your y variable is velocity. That equals your slope, which we now know the slope of the velocity time graph is the acceleration. By the way, this is final velocity here, right? Final velocity with nothing on it, just like we did before. With an O, it's initial. With nothing, it's final. So this is y equals your slope, your acceleration. Your x variable is the time, plus the y-intercept, which we now know is the initial velocity. Now, if you were to look this equation up in the book I'm not giving you, it would be written slightly differently. Addition is commutative, means you can change the order. So this is the way you would normally see it. Final velocity equals your initial velocity plus your acceleration times your time. Think about this. It's saying your velocity you end up with is the velocity you start with plus your acceleration times your time. But your acceleration times your time really tells you how much your velocity has changed. Rate of change of velocity times the time that it changed tells you how much it changes. So if you take your initial velocity, where you start, and add in how much your velocity changes, you get your final velocity. But before you get too happy with this equation and say, yay, we can use this on any motion, not really, right? Because this is a specific kind of motion. First of all, it was one-dimensional, straight down the incline. Secondly, look at this graph. Your velocity time graph is linear, and that means the slope is constant. And since the slope is the acceleration, it means that it is moving with one-dimensional, uniformly accelerated motion. And physicists use the word uniformly to mean constant. Okay, so uniform acceleration means constant acceleration. So this is an equation of uniformly accelerated motion. And in fact, that's the unit we're in. That's the model we're looking at here. We spent a whole unit looking at constant velocity motion. Now we're going to look at uniformly accelerated motion. And in this level, we're never going to get any deeper than that, because to deal with something that would have a curvy velocity time graph, you really need calculus, and we're not going to do calculus in here. We do that in APC. Right? So uniformly accelerated motion. Now that we know all this, you might remember from the original lab that we couldn't say what the slope of your position times squared graph was. In fact, in the post lab, we left a little blank there. We said slope equals blank. Well, now we know enough physics to be able to explain it. Check out your numbers. If you look at your velocity time graph slope that we just made in the lab extension, which is the acceleration, right? Look at that number. Now compare your position times squared graph slope. First of all, look at the units. It's in centimeters per second squared, just like the velocity time graph slope is, but it's not the exact same number. What is it? Look at those numbers. It's exactly half. So we can say that experimentally we just determined that the slope of a position versus time squared graph is 1/2 the acceleration. Go back in your notes to the original lab report and put that in that little blank. So it says slope equals 1/2 the acceleration. And when you're writing up the lab report and you get to the point where you're saying, hey, my slope is this number, just say, which is 1/2 the acceleration, and you've just explained the meaning of your slope. Now, I think that's kind of cool that we get that number like that, and we can see that in our numbers, that our slope of our position times squared graph was 1/2 the acceleration. But here's something I find even cooler. Let's look at this situation theoretically and do what we call a proof. So here's our original velocity time graph. Right? Linear goes through 0, 0 because we're starting from rest. We created a math model out of this. Right? The y variable is the velocity. Your slope is the acceleration. Your x variable is the time. And in this case, your y-intercept, your initial velocity, is 0. Right? So there's our equation. But you might remember that we don't only need to look at the slope and the y-intercept on a velocity time graph. There's something else that has physical meaning. Assume here that we start at a time t, and that means we're moving at we let it roll for a time t, at which point it's moving at a velocity v. Let me say that again. So let's say we let the disk go, and we look at it while it's rolling through a time t, at which point it will be moving with a final velocity v. Then besides looking at the slope and the intercept, which give us this equation, we could also look at the area under the curve. You remember doing that? If you look back at the constant velocity unit, we decided that the area under the curve of a graph of velocity versus time told you something about the motion of an object. It told you its displacement, its change in position. Right? And we don't need calculus to analyze this area. It's just a triangle. So the area is just 1/2 base times height. So in other words, the area is the displacement. The base of this triangle is t, so 1/2 times t, and the height is v. Think about how I just made that equation. Now, this doesn't look like anything yet, but we also know that the final velocity is the acceleration times the time. Substitute. Displacement is final minus initial position. 1/2 times time times, instead of final velocity, acceleration times the time. Now let's simplify. In our lab, the initial position at time 0, we were at position 0, so that cancels. And t times t is t squared. So final position is equal to 1/2 acceleration times time squared. That's what theoretically the equation should be. Now you might be saying, so what? Nice equation, great, we could plug numbers in and find stuff. Well, let's compare that. Oh, by the way, that's when the initial velocity is 0, right, only. Let's compare that to the results of our original lab. Here was our graph of position versus time squared, which was linear. We created an equation that looked like this, where this number was the slope of your position time squared graph. We created that by doing y equals mx plus b, right? Well, now compare that to the equation we just theoretically derived. Look at the y. In both cases, experimentally and theoretically, the y is the position. Look at the x variable. In both cases, experimentally and theoretically, it's time squared. Look at the y-intercept. In both cases, it's 0. So that means that both experimentally and theoretically, the slope of the graph must be 1/2 of the acceleration. Now, if that doesn't blow your mind a little bit, I don't know what will. So what we've just, oh, thank you very much. I appreciate the applause. What we've just done there is showed both experimentally, up here, and theoretically, down here, that the slope of a position times squared graph has to be 1/2 the acceleration. We've just showed here that experiment and theory match. That's science. That's what we want to be able to do. We want to be able to make predictions based on theory that actually match reality. And we want to be able to take predictions that we find in reality and find theories that explain them. That's what we've just been able to do over the last few days. And that's something you haven't done much of in science. And that's something that we're going to do a lot more in physics. And that's, I think, one of the cool but geeky things that we can now do. So if that blew your mind a little bit, rewind it and watch it again, because it's a beautiful thing. And I hope you've enjoyed this lab extension post-lab.